Welcome back to Talk Tensors. Today we're taking a deep dive into something pretty cool. A paper called Meta-Learning for Physically Constrained Neural System Identification.
Yeah, no, it's a bit of a mouthful, huh? But don't worry about trying to remember the whole thing. We'll just call it the Meta-Learning paper for short.
Sounds good to me. So tell me, what's this paper all about?
It's about solving a really tough problem, actually, that comes up all the time when you're trying to model systems, especially when you don't have a lot of data to work with.
Oh yeah, I think a lot of our listeners can relate to that. Whether you're training a model or just trying to figure out how something works, that limited data thing can be a real roadblock, right?
Exactly. So picture this. You're trying to build a model for something like, let's say, an HVAC system in a building. You want to be able to predict, like how the temperature and the airflow and all that's going to change over time. Now, the traditional way to do this, you'd need mountains of data from that specific HVAC system to train a good model.
Right. But I bet in the real world, you don't always have that much data from a specific system.
You got it. That's where this whole meta-learning thing comes into play. What if we could use data from other similar systems, like other HVACs and other buildings, to get a head start?
Oh, so you're using information from those other systems to help the model learn faster.
You got it. That's the basic idea. Now, in this paper, they use something called a neural space model, or NSSM, to represent the system.
Okay, state space model, NSSM. Remind me what those are again?
Basically, it's a fancy way of saying that we're using a neural network to capture the relationship between the inputs and outputs of the system over time.
Okay, and they call it a state space model because...
You just are not just looking at the inputs and outputs directly. We're also trying to model the internal state of the system, which captures all the important information that's evolving over time.
So like with the HVAC example, the state might include things like the current temperature, the fan speed, the humidity, all those kind of things.
Exactly. You're catching on quickly. And the NSSM basically learns how all those internal states change based on the inputs to the system.
So you're saying the NSSM acts like a translator, taking the raw data from the system and turning it into a language the neural network understands.
Exactly. And it uses that language to make predictions about what's going to happen next. But like we were saying before, usually you need a ton of data from the specific system you're interested in to train these NSSMs really well.
Right. And that's where the meta-learning idea comes in, trying to overcome that data limitation. So how does meta-learning actually work?
It's a bit like giving the model a crash course in system dynamics. You train it on a bunch of different source systems so it learns how these systems tend to behave in general.
So it's almost like showing the model different variations of the same problem, right?
Yeah.
So it gets better at picking up on the underlying patterns.
Exactly. That way, when you encounter a new system, the model's already got a head start. It can adapt much faster, even with just a little bit of data from that new system.
I'm starting to see how this could be super useful in the real world. But you also mentioned earlier that the authors take things a step further by incorporating the laws of physics into their model.
Right. That's where things get really interesting. Instead of just letting the model learn from data blindly, they're basically saying, hey, you need to obey the rules of physics too.
Okay, that sounds pretty cool. So how do they actually make the model obey the laws of physics? I mean, can you really teach a neural network physics?
Well, it's not like we're giving it a textbook. It's more about building those physical constraints directly into the structure of the model.
So they're kind of baking those physics rules into the model from the get-go.
Precisely. For example, think about a robot arm. It can only bend so far, right? We can build that limitation into the model so it doesn't predict physically impossible movements.
I'm starting to see how this makes the model not only more accurate, but also more trustworthy, because its predictions are grounded in the real world.
Exactly. And it turns out there are different types of constraints we can use depending on the system. They talk about polytopic constraints and vector field constraints in the paper.
Okay, those sound a bit intimidating. Can we break those down a bit?
Sure. Polytopic constraints are kind of like setting up boundaries or limits for the model's predictions.
So it's like saying, hey, model, you can make predictions, but they got to stay within this range, within these limits.
Exactly. For instance, if you're predicting the temperature in a room, it can't go below absolute zero, right? And it probably shouldn't exceed some crazy high value either.
Makes sense. So you're essentially giving the model some guardrails, making sure it doesn't go off the rails and predict something totally nonsensical.
You got it. And then there are vector field constraints. These are important when you're dealing with things that have both magnitude and direction, like a magnetic field or fluid flow.
Oh yeah, because those things aren't just about how strong they are, but also which way they're pointing.
Exactly. And the authors use some pretty clever math, including a result called Theorem 1 and a specific activation function called the swish function to ensure that the model's predictions for these vector fields obey the laws of physics.
I'm sensing a theme here. They're really pulling out all the stops, combining all sorts of tools from math and physics to make this work.
It's a really elegant approach, and what's really cool is that they actually test their ideas on real-world problems, not just in theory.
Right. I remember you mentioned they have some pretty interesting case studies in the paper.
They do. They show how their framework can be used to model things like HVAC systems and robots navigating using magnetic fields, even when data is scarce.
Wow, so they're actually showing how this could work in practice.
Exactly. And the results are pretty impressive. But before we jump into those case studies, I think it'd be helpful to take a little detour and talk about how we got here. Like, what are some of the key ideas that led to this research? What's the history behind this whole field?
Yeah, that's a great point. Let's take a little trip down memory lane and see how all this came to be.
Sounds good to me. So, early attempts to use neural networks to model systems. Well, they're pretty limited, to be honest.
Why is that? What were the limitations back then?
Well, the neural networks themselves weren't as sophisticated, and we didn't have as much data to work with either. Plus, people weren't really thinking about incorporating physics into the models.
Ah, so it was kind of like trying to build a skyscraper with just twigs and mud.
Pretty much. But then came the deep learning revolution.
Yeah, it's like everyone suddenly realized, hey, if we give these neural networks more layers and more data, they can do amazing things.
Exactly. And around the same time, people started realizing that, hey, maybe we shouldn't just throw data at these models and hope for the best. Maybe we should also teach them something about the physical world.
So it was like a shift from just mimicking data to actually trying to understand the underlying physics behind the data.
You got it. And that's when things really started to take off. And then along came meta-learning, which took things to a whole other level.
Right. Meta-learning, this idea of training models that can learn how to learn.
Exactly. And that's what this meta-learning paper is all about. It's like the culmination of all these different ideas, deep learning, physics-based constraints, and meta-learning all coming together in a really elegant way.
Wow. It's really cool to see how all these pieces fit together. It's like we're witnessing a paradigm shift in how we approach system modeling.
I agree. And what's exciting is that we're just at the beginning. There's so much more we can do with this.
I'm excited to see where it all leads. But before we get ahead of ourselves, let's rewind a bit and talk about the basic setup for neural system identification. I remember seeing a bunch of equations at the beginning of the paper. What were those all about?
Ah, yes. They lay out the mathematical groundwork. The basic idea is to represent a system's behavior using equations. You have inputs, which are like the things you can control or change in the system.
Like the settings on that HVAC system.
Right. Exactly. And then you have outputs, which are the things you're trying to measure or predict, like the temperature in the room. And we can use equations to describe how those inputs affect the outputs over time.
Okay, so we're basically trying to capture the cause and effect relationship between the inputs and the outputs using math.
Exactly. And the authors use equations 1, 2, 3, and 5 to show this. They also define something called a loss function, which is a way to measure how well our model is doing at predicting the outputs based on the inputs.
So the equations are like a way to translate the real-world behavior of the system into a language that the neural network can understand. And the loss function tells us how one of the network is speaking that language.
Perfect analogy. And remember, they're using the specific type of neural network called a neural state space model, or NSSM, to represent this whole relationship.
Right, the NSSM. So can you remind me again, what are the key parts of the NSSM and how do they work?
Sure. The NSSM has three main components: an encoder, a state transition operator, and a decoder. Think of them like different parts of a machine that work together.
Okay, I like that. So what does the encoder do?
The encoder takes the raw input data from the system and compresses it into a more compact representation.
So it's like summarizing a long paragraph into a few key bullet points.
Exactly. It's finding the essential information that the network needs to understand what's going on in the system.
Got it. And what about the state transition operator?
That's the heart of the NSSM. It takes the compressed information from the encoder and uses it to predict how the system's internal state is going to change over time.
So if we know the current temperature in the room and the thermostat setting, The state transition operator can predict what the temperature will be in 5 minutes.
Precisely. And finally, the decoder takes that predicted internal state and translates it back into something we humans can understand the output we care about, like the future temperature in the room.
So it's like taking those bullet points from the encoder and expanding them back into a full paragraph.
Exactly. And what's really neat is that they also show in figure 1 of the paper how this whole structure of the NSSM can change depending on the type of data you have available.
So if you have more detailed information about the system, you can tweak the NSSM to take advantage of that.
Exactly. But remember, as we talked about earlier, training these NSSMs will usually requires a ton of data from the specific system you're interested in.
Right, which is why the meta-learning idea is so powerful. It allows us to leverage data from other similar systems to train a model that can adapt quickly to new ones.
Exactly. It's like giving the model a broader education in system dynamics so it doesn't need to start from scratch every time.
That's a fantastic way to think about it. So now that we've covered the basics of neural system identification, can you walk me through how they actually implement meta-learning in this context?
Absolutely. And this is where the paper gets even more interesting. But before we go there, let's take a quick break and we'll come back to delve into the details of their meta-learning approach. All right, so picking up where we left off, remember how we talked about meta-learning being like giving the model a crash course in system dynamics?
Yeah, training it on all sorts of similar systems so it can learn how to adapt quickly.
Right. Well, the authors of this paper use a specific meta-learning algorithm called model-agnostic meta-learning, or MML for short.
MML, okay. And how does MML actually work?
It's all about this idea of a two-loop training process. You've got an inner loop and an outer loop.
2 loops, huh? Okay, what happens in each loop?
In the inner loop, you basically fine-tune the model on a specific source system. It's like imagine you're teaching someone to ride a bike.
Okay, I like analogies, so I'm following you.
Each source system is like a different type of bike, maybe a mountain bike, a road bike, a BMX bike, you name it.
So the inner loop is like practicing on each individual bike.
Exactly. The model learns how to handle the quirks of each one. And you've got the outer loop. The outer loop takes a step back and looks at how well the model can generalize across all those different bikes.
So the outer loop is evaluating the rider's overall biking skills, no matter what bike they're on.
Exactly. It's all about making sure the model isn't just memorizing how to ride one specific bike, but actually learning the underlying principles of biking.
That makes a lot of sense.
Yeah.
So with MML, we're basically training the model to be a quick learner, able to adapt to new systems easily.
Precisely. Now, remember how we mentioned ANIL earlier? Almost no inner loop.
Yeah, ANIL. You said it was about making the whole process more efficient.
Right. So instead of updating every part of the model in the inner loop, with ANIL, you only focus on adapting certain components.
So it was like saying, okay, we don't need to reteach the rider how to balance, just how to adjust to the handlebars on this new bike.
Perfect. You got it. And that saves a ton of time and computing power.
That's super clever. So MAM and NIL, those are the meta-learning techniques. Now, let's talk more about those physics-based constraints. You were saying that's a key part of making these models more realistic.
Absolutely. It's not enough to just train a model on data. You got to make sure it understands the rules of the game, right?
Yeah, the rules of physics. So you mentioned polytopic constraints and vector field constraints. Let's start with polytopic constraints. Can you remind me what those are all about?
Polytopic constraints are basically about setting limits on the model's predictions. It's like drawing a box around the possible values.
So like saying, you can predict anything you want, but it has to stay within this box.
Exactly. Think about it like this. If you're modeling the pressure in a pipe, we know it can't go below 0, right?
Right. That wouldn't make any physical sense.
And there's probably also some upper limit, some maximum pressure the pipe can handle before it bursts.
Okay, so the polytopic constraint would say all your pressure predictions have to stay between these two values, the minimum and the maximum.
You got it. And they use a technique called ray representation to enforce this, which basically makes sure that the model always stays within those bounds.
That's really neat. It's like building a safety net into the model.
Right, so it doesn't predict anything crazy. Now, vector field constraints, those are a bit more complex.
Yeah, those sounded more challenging.
They're important when you're dealing with systems that involve things like magnetic fields or fluid flows.
Right, the robot navigating with the magnetic field, that was a good example of that.
Exactly. Now, we know from physics that these kinds of fields can't just have any random swirls or rotations in them.
Right, they have to follow certain rules, certain patterns.
Exactly. For example, magnetic fields have to be what we call curl-free.
Curl-free. Oh.
It's a physics thing, but basically it means the field can't have any weird loops or eddies in it.
So the vector field constraint is saying whatever you predict about this magnetic field, it has to obey this curl-free rule.
Exactly. And to do this, they use something called Theorem 1, which is this really important result from vector calculus. They also use a special activation function called the swish function.
I'm noticing a trend here. They're using all sorts of high-powered math and physics to make this all work.
It's a beautiful blend of different fields. And remember, it's not just theoretical. They actually put these ideas to the test in real-world scenarios.
Right, those case studies. You mentioned one with an HVAC system and one with a robot navigating using magnetic fields.
Exactly. So let's talk about those, shall we? The first one, the HVAC system, they were trying to model a system where they didn't know the exact amount of refrigerant.
Okay, so a real-world problem where you might not have all the information you need up front.
Right. And to train their model, they used a high-fidelity simulator to generate a bunch of source systems with different amounts of refrigerant.
Ah, so they're creating a bunch of virtual HVAC systems to train the model on.
Exactly. It's like creating a virtual playground where the model can experiment and learn without having to mess with real HVAC systems.
I like that, a virtual playground. So how well did it work? Did the model actually learn to predict the behavior of the real HVAC system, even though it didn't know the exact amount of refrigerant?
It did. They tested their model on a real HVAC system, and even with limited data, it was able to accurately estimate the system's state. And you know what's really cool?
What's that?
They actually compared their model's performance to a traditional model that wasn't trained using meta-learning.
Okay, and how did it stack up?
Their model blew the traditional one out of the water. They even have a nice graph in the paper, Figure 6, that shows just how much better it performed.
Wow, that's impressive. So even with limited data, their model, with all its meta-learning and physics-based constraints, was able to outperform a traditional model that didn't have all those bells and whistles.
Exactly. It really shows the power of their approach. Now, the second case study, the one with the robot navigating using magnetic fields, that one's really cool too. Remember how we were talking about each building having its own unique magnetic fingerprint?
Yeah, like a magnetic signature?
Right. And that makes it hard to train a model that can generalize across different buildings.
Because if you train it on one building, it might not work well in another one.
Right, exactly. But what they did was they trained their model on a bunch of simulated buildings, each with its own magnetic field map.
So like the HVAC example, they're creating a virtual playground for the model to learn in.
Exactly. And by exposing the model to all these different magnetic environments, it was able to learn the general principles of magnetic localization.
It's like teaching it to read a magnetic map, not just memorize a specific route.
Exactly. And when they tested their model in a new building, it was able to accurately track the robot's position, even though it had never seen that building before.
That's pretty amazing. It really shows how meta-learning can help models generalize to new situations.
I agree. It's a really powerful technique. But I think what's even more exciting is what this research points to for the future.
Yeah, where do you think this all leads? What are some of the novel notions that come to mind after reading this paper?
This paper really gets you thinking, I mean, the stuff they're doing with HVAC systems and robots is already pretty impressive, but, what if we could scale this up?
Yeah. What if we could apply these ideas to even bigger, more complex systems?
Right. Imagine trying to model something like a whole power grid or like a super intricate manufacturing process with tons of interconnected parts. That'd be wild.
That would be a huge challenge, but if we could pull it off, the benefits would be massive.
Absolutely. And another thing that comes to mind, all the systems they were modeling in the paper, they were pretty much static, right? Like they didn't change that much over time.
Yeah, that's true. But what about systems that do change over time? Like what if you're trying to model a robot arm that's slowly wearing down from use? Or a traffic network as a city grows and changes?
Exactly. That adds a whole other level of complexity.
Right. The model have to be able to adapt not just to different systems, but to how a single system is changing over time. It's like learning to drive a car that's constantly evolving. The steering wheel gets looser, the brakes wear down.
That's a great analogy. It'd be like playing a video game where the controls are changing all the time. You got to be constantly learning and adapting.
That's wild. So how would we even begin to model systems like that? Where do we even start?
Well, I think one key is to find ways to incorporate information about how the system is expected to change. Like, if we know the robot arm is likely to wear down in certain ways, we can build that into the model.
Ah, so give the model some knowledge about the aging process, so to speak. Make it aware of how things tend to change over time.
Exactly. And, another thing I was thinking about, we've been focusing a lot on these specific types of physics-based constraints, like the polytopic constraints and the vector field constraints.
Yeah, it has. It's pretty mind-bending.
But there are so many other physical laws and principles out there that we could potentially leverage. Like, think about conservation of energy or momentum or thermodynamics.
Oh, yeah. All those fundamental laws of physics that govern how things work. So we could potentially bake those into the models, too.
Exactly. Imagine the possibilities. We could create models that are not only super accurate, but also guaranteed to obey the laws of physics no matter what.
That's really cool. It feels like we're just starting to explore this whole space of physics-informed machine learning,
Yeah.
and the potential is huge.
It is. And I had one more thought. What if we could bring humans into the loop?
Oh, interesting. How do you mean?
Well, what if we could design systems where human experts could provide feedback to the meta learner, guide it in the right direction?
Ah, so it's like a collaboration between human intelligence and machine learning.
Exactly. Like, imagine a human mentor working with the meta learner, helping it avoid pitfalls and learn more efficiently. I think that could be really powerful.
That's a fascinating idea. It's like combining the best of both worlds.
Right. I think we're just at the tip of the iceberg with all this. There's so much more to explore.
I completely agree. This paper has definitely opened up a whole new way of thinking about system modeling.
It has. And I'm really excited to see what the future holds for this field.
Well, that's all the time we have for today's deep dive into the world of meta-learning and physics-informed machine learning.
We hope you learned something new and maybe even got some ideas for your own research.
And remember, dear listeners, keep those tensors talking.